So now to understand how we can measure what happens to oscillations of a sequence as n gets larger and larger, let's again return to the example that we have already considered. And that would be this example of the sequence Sn equal to -1 to the n over n. So we have this question. How can we measure what happens to oscillations of Sn equal to -1 to the n over n as n gets bigger. So one thing that we can do, the sequence Sn, right, is also a set. So I'm going to consider Sn as a subset of R. So if I look at my sequence starting from the beginning, from the first element, and I think about the oscillations that the sequence undergoes, what I can do is I can take a supremum of the sequence and the supremum and the infimum of the sequence, and this will tell me how large the elements of a sequence can get and how large a negative they can get, for example. So by taking, so we can estimate this window by taking infimum, a window of oscillations, by taking infimum and supremum of this set Sn. So thinking about oscillation still, we can take supremum of Sn and infimum of Sn. Then all elements of Sn lie between inf Sn and sup Sn. And therefore, the interval from inf Sn to sup Sn provides the window of oscillation for the entire sequence. And so in this case, So in this example, infimum of -1 to the n over n, we need to determine that, and also supremum of -1 to the n over n. How do we find infimum? So the sequence starts at, again, S1 is -1, S2 is 1/2, S3 is -1/3, etc. So we see that what happens with these numbers, they switch a sign from negative to positive, and at the same time they decrease in size, right? Because the first element is size 1, second size 1/2, the next one is 1/3, and so on. So if I take a supremum over the entire set, let me list one additional number here. S4 is 1/4. Every time I oscillate back up, I come back to a smaller value, right? So that means that the first value must be the largest. And so S2 equal to 1/2, that will give me a supremum of my set. What about the infimum? Same story holds. First, you're at S1, you're at -1. Then next negative number is S3, that is -1/3. Again, it's going to be smaller in size, but because the size of the sequence, the modulus, absolute value of the sequence decreases with n. So it means that the first element that I see is going to be the smallest, and so infimum of -1 to the n over n must be -1. All right, so the sequence is, entire sequence leaves between -1 and 1/2 in this case. And the question is, how good of a measure of the window of oscillation is this going to be? Not really a very good one, because the largest element, largest negative element is the first one, largest positive element is the second one. So if I want to decide, if I want to see what happens with the tail of my sequence, then really the information about the first and the second element should, at the end of the day, be irrelevant. So what we're going to try to do, we're going to try to do this. I'm going to say, so here I'm taking infimum over my set Sn when n is greater or equal than 1. N is greater or equal than 1 for the supremum. So once again, if I want to see how the things are oscillating at infinity, really the size of the first two elements is not very important. And so then instead, let's try to take an infimum when n is greater or equal than 2, starting from a second element of the same guy. And I also want the supremum starting from the second element. N greater or equal than 2. And again, -1 to the n over n. So what are the infimum and supremum here? Again, some story is going to hold. The largest negative element is going to be above, with an index larger than 2. So if you start at 2, first element is positive, next element is negative. The first positive element is the largest, and the second remaining element, or the third element of the sequence, is going to be the smallest. So the infimum then is -1/3, and the supremum is equal to 1/2. So once again, on the first step, I take supremum and infimum of the entire sequence. Now, on the second step, I'm taking supremum and infimum of a sequence starting from the second element. I discarded the first one. I'm saying that if I want to study what happens to my sequence as n goes to infinity, whatever happens to the first element is totally irrelevant. But then if I chopped off the first element, I'm left with 1/3, -1/3, and 1/2 as my new window of oscillations. And again, I notice that infimum and supremum, the largest and the smallest element of my sequence, occur at the beginning of the remaining sequence, at 2. So again, they should be irrelevant in terms of specifying how the sequence is going to oscillate as n goes to infinity. So we're going to do the following thing at the next step. So now I'm going to get rid of S1 and S2 and take infimum and supremum starting from n equal to 3. So let's do that. And how are things going to change? They're going to change in the following way. If we take infimum starting from 3 and supremum starting from the same point, again, if I go to these elements that I listed here, if I start from the third element and I ignore the first two, then the smallest value is going to be, of course, -1/3, and the largest value is 1/4. So -1/3, and this guy is 1/4. So that means that if I look at my sequence after I remove the first two elements, then I will see that the sequence is going to be oscillating between -1/3 and 1/4. When I look at the sequence starting from the first element, the window of oscillations was from -1 to 1/2. So now it is from -1/3 to 1/4. And I can continue doing exactly the same thing. So I can just argue again that -1/3 is a third element, 1/4 is a fourth element of my sequence. Again, they do not really determine what's going on with the sequence as n gets bigger. So I can repeat the same process. I can discard the first 3 elements and start taking infimum and supremum starting from the fourth one. And I can continue doing this. And in this case, let's say we're taking infimum starting from n greater or equal than k instead. And I want to figure out what that is, and I also want to do the same for this thing with the supremum. Well, what shall we see here? We will see that if n is, let's say, if n is even, sorry, not if n, but if k is even, then the sequence will look like -1 to the k is going to be 1. So I'll see 1 over k, 1, -1 over k plus 1, right? Because if k is odd, -1 to the k plus 1 is -1. Then 1 over k plus 2, etc. If k is odd, right, and I'm starting to look at my sequence from the kth element, then the first element, if I start from a kth element and k is odd, first element I will see, I'm going to get -1 over k. Second element is positive 1 over k plus 1, -1 over k plus 2, and so on. And so then if I'm taking the infimum starting from the kth element, if n is even, then the first element is positive, second element, next element, or kth element is positive, k plus first element is negative. And it has a larger size of the remaining elements of the sequence. So that means that what I'm going to get for an infimum is going to be minus 1 over k plus 1. If k is even. And if k is odd, then the first element is negative, and it has a larger size, so minus 1 over k if k is odd. All right, and I can do a similar thing with the supremum. So let's see what we get in this case. So taking a supremum when k is even, the first element is positive and it's the largest in size. So 1 over k if k is even. And then if k is odd, the first positive element is 1 over k plus 1, and that element is going to be the largest. All right. And so then from this, what sort of thing can I observe? If I keep chopping off the elements of a sequence, then take supremum and infimum of the resulting, of the remaining elements in a tail of a sequence starting from a kth one, starting from the kth element. Then infimum is a number, a negative number that is getting smaller and smaller in size. And the supremum is a positive number that is getting smaller and smaller in size. So if I chop off k initial elements and I take infimum and supremum of the resulting terms in my sequence, as k gets bigger, infimum and supremum are getting closer and closer to 0. So that means that the window of oscillations actually is getting smaller and smaller as k goes to infinity. So the conclusion, the window of oscillations for Sn goes to 0 as n goes to infinity. And so from that, of course, I can deduce that the sequence Sn converges. Not just converges, but converges to 0, because it oscillates around 0 within the window which has a width 0, and so the sequence must converge to 0 in this case. Alrighty. For example minus 1 to the n, so I'm going to repeat this. For just minus 1 to the n. So what I have in this case, I will need to take infimum, well, actually, let's do it in the same way as before. What if I take a supremum of the entire sequence? Supremum n is greater or equal than 1 of minus 1 to the n, and the infimum n greater or equal than 1 of minus 1 to the n. I mean, it's easy to see, right, that both that the supremum is going to be 1 because the sequence is oscillating between minus 1 and 1, and infimum also is equal to 1. If I take supremum n greater or equal than 2 of the same thing, then series is still oscillating between minus 1 and 1, so I chopped off the first element. But infimum and supremum are still going to be the same, right? Because the largest element is still 1, and the smallest element is still going to be minus 1. I can keep going like this. I can keep chopping off the elements from the front of my sequence and continue taking suprema and infima. So supremum n greater or equal than k of minus 1 to the n, and infimum n greater or equal than k of minus 1 to the n. The sequence still is oscillating, even though I chopped off the elements from the beginning. It just continues doing the same thing. It goes from minus 1 to 1 and back. So that means that this supremum is still 1, and this supremum is still 1. This infimum is minus 1. And so in this case, as k tends to infinity, the window of oscillations stays the same it remains minus 1, 1. Right, and therefore, in this case, because the sequence continues to oscillate between minus 1 and 1 forever, that means that the sequence does not converge. So it does not converge as n goes to infinity. So what I want you to take out of this is the following: that if I want to find the window of oscillations in the tail of my sequence as n is getting bigger and bigger, what I would need to do is to chop off more and more elements from the beginning of the sequence and continue taking suprema and infima. And that, I continue looking for the greatest lower bound and the least upper bound of the remaining terms in the sequence. And as I keep doing this, at the end of the day, what happens to the supremum and infimum will tell me how my sequence is oscillating. So in order to make these ideas precise, let's do the following construction. Suppose that we have a sequence Sn. What did I do with the sequence Sn? I considered two things. Chop off the first element, chop off the, so take the first element of your sequence, take it away, and take supremum and infimum of the remaining part of the sequence. Chop off the second element, do the same thing. Chop off the third element, do the same thing. So I'm going to define two new sequences. I'm going to call the sequence U K to be the infimum. Let me just make sure that I use the same notation as a book. Right. So I'm going to make UK an infimum when n is greater or equal to, in fact, in this case, I'm going to make it just, let's do greater or equal. N is greater or equal than k of Sn, and Vk to be the supremum, n greater or equal than k of Sn. So notice that UK and Vk are precisely the quantities that I considered above. So for k greater or equal than 1. Right, so if k is equal to 1, I take infimum as supremum of the entire sequence. K equal to 2, I take infimum as supremum of a sequence without the first term. K equal to 3 without first and second term, and so on. So then UK and Vk are going to be sequences of real numbers. Okay? So UK to Vk defines a window within which my sequence is going to be oscillating, starting from an element k. What I want to do if I want to measure the window of oscillations at infinity, so what happens to my window of oscillation as k gets bigger and bigger, what I would need to do is I will need to take a limit of uk and a limit of vk as k goes to infinity. Well, but before I do that, let me consider the following situation. So let's do this separately here. Let's suppose that I have a set, capital S. This is maybe a subset of the set of real numbers. And I have the set S1, and S1 is a subset of S. Right, so all elements, all real numbers in S1 are also contained in S, but not vice versa. And the question is, if I take infimum of S and I take infimum of S1, would I be able to relate these? If I take supremum of S and I take supremum of S1, can I relate those? Well, let's think about it. What is infimum of S1? So infimum of S1 is the greatest lower bound of S1. Infimum of S is the greatest lower bound of S. Now, what is true about S versus S1? S1 contains less elements, or S contains potentially more elements because S1 is a subset of S. So now if I have to take the infimum of the set which contains more numbers in it than the average set, well, what can happen to the infimum? Can infimum of a larger set be bigger? And the answer is no, right? Because all elements in the smaller set are elsewhere in the larger set. So that means that all those elements are still bounded from below by infimum of S1. And then S has more elements. So some of these elements can be larger than this infimum, and some elements can be smaller. If I look at elements which are larger, uh, then they do not affect the lower bound, right? Because if S1 has a lower bound and I start adding to S1 elements that are larger than this lower bound, the lower bound is not going to change. But if I add elements which are smaller than this lower bound, then of course the lower bound will not be a lower bound anymore, and it will have to be reduced. And so the point of this is that if I take infimum of the larger set, then that infimum must be less or equal than the infimum of a smaller set, because larger set can contain even smaller numbers than S1. If it doesn't, then the infimum is not going to change. But if it does, the infimum is going to lower. So there is this inequality, less or equal, between two infima. And a similar thing should happen to the suprema. If I have a set capital S, and I take a supremum of this capital S, and then I start removing elements. So if I remove an element from a capital S, what will this do to the supremum? So either this element itself is equal to the supremum, and if I remove it, then the supremum of a set is going to be potentially lower. Or this element is smaller than the supremum, smaller somehow. In that case, the supremum is not going to change. So what I'm saying here is that if you think about it, as you keep removing elements from the set, the only thing that you can do is to lower the supremum, not to increase it. Because if a supremum gets bigger when you remove an element, that means that the set should contain some elements that are bigger than the original supremum. And that does not make any sense. So the smaller set then should have a smaller supremum. So the sign is going to be greater or equal here. I will encourage you to try to write the formal proof of this fact that I just mentioned, but I don't have time to do it. So just I'm just giving you the reasonings why these inequalities will hold. All right. So then, if this is true, we're going to notice the following. That if I think about two sets, one set is going to be Sn n greater or equal than k, and another set is going to be Sn n is greater or equal than k plus 1. What can I say about those sets? Are they related in any way? The answer is yes, because Sn has elements starting from a k1, Sn, so this set has elements starting from a k1, this one has elements starting from a k plus first, so the circled set will have one fewer element than this first set. And so that means, because it has fewer elements, but all other elements belong to both sets, that this is a subset of that. And as a result, we can conclude of the result that I just mentioned here. We can conclude from this that infimum of Sn n greater or equal than k, this must be, so the infimum of a larger set must be smaller, less or equal, than the infimum of Sn. Okay, let's see, that's the opposite actually. n greater or equal than k is going to be the larger set. So if it is a larger set, it has a smaller infimum, right? So it's less or equal than infimum n greater or equal than k plus 1 of Sn. And likewise, supremum as n is taken to being greater or equal than k, supremum of Sn versus supremum n greater or equal than k plus 1 of Sn. The set on the right is smaller, so its supremum must be smaller, so greater or equal. Well, but then what are these infima and suprema? The first one, infimum of Sn when n is greater or equal than k, I call that uk. So this is uk. And then if I use the same definition starting from k plus 1, this term must be uk plus 1. And similarly, if I'm taking supremum of Sn, I call that vk. And then this guy would be vk plus 1. So what are we concluding from this? And this should be true for any k, right? So for any k greater or equal than 1, and this is true for any k greater or equal than 1. So uk is less or equal than uk plus 1, vk is greater or equal than vk plus 1. So the conclusion from this is that the sequence vk is monotone decreasing, right? Because vk's are getting smaller. And the sequence uk, this guy is monotone increasing. But we know that any monotone sequence converges. And so from here, monotone, let's call it a theorem about monotone sequences. From this theorem, it follows that both vk and uk converge as k goes to infinity. And so limit as k goes to infinity of uk exists and equal to some number or infinity. I'm going to, so let's actually, so this guy exists. What does that mean? It means that the limit as k goes to infinity of what? What was my uk? uk is infimum as n is greater or equal than k of Sn. So this is a limit of the infimum n greater or equal than k of Sn. So this is equal to some number, and or number or infinity. And I'm going to denote this, so this guy exists. Denote this by just combining limit and infimum and saying lim inf as n goes to infinity of Sn, or lim with underscore n goes to infinity of Sn. And this is called limit inferior or liminf of a sequence Sn. So and call this quantity limit inferior of Sn, right, of the sequence Sn. And I can do the same thing with vk. So let's just copy this. And so I need to replace uk with vk and infimum with the supremum. So again, vk is monotone increasing, so its limit exists. Replace vk by its definition sup n greater or equal than k of Sn. This limit exists. Instead of saying liminf, now we're going to say lim sup. And or limit with a bar above the limit. And so this would be a limit superior of Sn. The important thing is that because it doesn't matter what the sequence Sn is, uk and vk are monotone sequences, so these limits exist, then it follows that both limit n goes to infinity of Sn and lim sup as n goes to infinity of Sn, they always exist. Even if your sequence does not converge, lim sup and lim n would exist. All right, so then one more fact here. So lim sup, or rather, let's start from liminf. Liminf n goes to infinity of Sn to lim sup n goes to infinity of Sn. This is equal to the limiting window of oscillations for my sequence Sn. Right, so I hope that this makes sense, because that is how we came up with this idea of liminf and lim sup. What did we do? We keep chopping off the elements of a sequence, and we keep taking supremum and infimum. The more elements I chop, the closer then is infimum and supremum are going to represent how my sequence is oscillating. And so then from this I can also see a fact I'm going to prove in the next lecture, that if a limiting window of oscillations actually is going to have lim inf and lim sup being the same, then that means that actually the sequence converges, because if the sequence must exist between two numbers, must at infinity, it must sit between two numbers, lim inf and lim sup, and those numbers are exactly actually the same, then the sequence converges. If they are not the same, that means that the sequence must be oscillating as n goes to infinity, and lim sup and lim nth will predict the range of those oscillations. So we're going, as I said, we're going to do a few examples and then continue with the theory of lim sup and lim nth in the next lecture.